everyone to our second or to our afternoon sessions. Today, now we have two sessions on messaging, or as Eurocrypt likes to call it, real-world crypto. Our first session will be by Lea Thiemt. Lea is a PhD student at the Nürnberg, working with Paul Rösler on secure messaging. And today she will be talking about generic anonymity wrapper for messaging protocols. This is an improvement and a generalization of the signal sealed sender protocol.
Yeah, thank you, Laura, for the introduction. This is joint work with Paul, Alex, Rolf, and Evgeny, and Rolf will also be doing a talk later. So this work is currently in submission, so maybe there'll be an e-printout soon. As the title says, I'm going to show you how we constructed a protocol which hides metadata of underlying messaging protocols and thus makes communication anonymous. I will start with introducing why we want to hide metadata. Right. So when Alice and Bob communicate over their favorite messenger, their content is end-to-end encrypted. That means Alice and Bob share some key material such that Alice can encrypt her message, send it to the server will forward it to Bob, and he can then decrypt the message, and nobody else except those two users can read the content. But that's not the only information that's being transmitted. Modern messaging protocols often also attach metadata such as sender and receiver ID or sequence numbers to the ciphertext, which then can be used to infer personal information about the users, such as their social graph, their location, or their daily routine. And this can be used to identify certain users and is particularly threatening for vulnerable groups such as activists or journalists. And that is why we want to hide metadata. And instead of looking at individual messaging protocols and adapting them to not contain any metadata, we want to create a generic wrapper, which can be used on top of existing messaging protocols to hide this metadata. Right, so let's look at our threat model. We assume that an adversary can see all the traffic which is on the network. And we also allow the adversary to temporarily expose user state. And we still want that previous communication is anonymous and the anonymity of future communication can be restored. Right, and before I show you our construction, I want to provide some background on secure messaging. So again, when Alice and Bob want to communicate, they share some key. Alice uses this key to encrypt her message and sends it over to Bob, who can then decrypt it. She does this for all her messages. But now the problem with this is, if there's only one shared key, then as soon as an adversary exposes this key, the adversary can read all the messages, all future and all past messages. So what modern messaging protocols do is, instead of using one key for all of the ciphertexts, they derive one key for each new message. So Alice and Bob start with some chain key. Then Alice derives some new chain key and some encryption key. She uses the encryption key to encrypt her message, sends the ciphertext to Bob, who can then decrypt it. After this operation, Alice and Bob will both discard their key material so that when an adversary exposes their state, previous communication still remains secret. Great, so Alice will continue doing this, deriving keys, sending messages, and so on. Now, this part roughly corresponds to the symmetric part of the double ratchet, and we can also find it in group protocols, for instance, in the sender keys protocol, where the sender in the group shares key material, symmetric key material with the other users in the group, and then all users can derive the sender's key material from this initial secret. Now, to restore confidentiality, if the secret is exposed, Alice and Bob can agree on new key material. And this is roughly corresponding to the asymmetric part of the double ratchet, where Alice sends some new public key material such that new, fresh keys can be derived. Great. Now, this works very well if everything derives, every ciphertext arrives in order. But what happens if, for instance, a ciphertext gets lost or two ciphertexts get reordered? Well, what Bob then does is, in case he receives the third ciphertext first, he will just derive his chain key, his key chain, until he arrives at the key which he needs for the third ciphertext. And he will discard all the prior chain keys, such that, again, an adversary who reveals the state cannot derive the key material for the third ciphertext anymore. Great, but Bob can still decrypt all out-of-order messages. Now, that is still not the whole story, because we assume that the encryption scheme is secure. So there's no way for Bob to tell which key to use for this third, for the ciphertext which arrives. And that is why where the metadata comes into place. For instance, in the double ratchet protocol, Alice will attach the index of the key and her public key for the next ratchet. So Bob then knows either if he has the key in the state, which key to use, or which key to derive to decrypt this ciphertext. Great, but this is exactly the metadata which we want to hide, because using this metadata we can already reveal patterns in communications and in sessions, and that is actually why Signal already has a solution for this. It's also a wrapper which is built on Bob's long-term identity key pair, and this is called sealed sender. So what Alice does is she takes the ciphertext and the metadata and re-encrypts it with Bob's public key. So Bob can then use this secret key to decrypt the message and continue decryption as before. Now, the problem with this, again, is, well, we have a wrapper protocol, which is great, but if an adversary now reveals the secret key, then the adversary can break all the anonymity of prior and future communication. And it's not only that the anonymity guarantees are not too good for this approach, but also this approach does not scale well for groups. That is, again, if we look at the sender keys protocol, which is used, for instance, in WhatsApp or Signal, Alice distributes this shared key material to all the users, and then she encrypts the message and sends it to all the users, so she only has one ciphertext. But now, if she uses the sealed sender protocol, she needs to encrypt this one ciphertext for each of the users again, which results in a linear communication overhead. So our wrapper protocol improves on this, and now I'll show you how our protocol works. Again, we build on top of some underlying messaging protocol which exchanges keys. So Alice and Bob start with the same key, and now Alice, again as before, derives the keys for each message, but what she also derives is for each key, she derives the pseudorandom looking tag. Yeah, that's all the magic. And then she can encrypt her ciphertext and just attach this tag to the ciphertext. The tag looks random, so an adversary cannot infer any information from this, what he sees, what they see on the network. But Bob still knows which tag to use, which key to use to decrypt the ciphertext. And this would be a replacement for sender keys and sealed sender. But we can also use it as a generic wrapper protocol, as I promised, for arbitrary messaging protocols. And that is, we just take this key material, which is established by the underlying key messaging protocol, and we derive a new chain key only for anonymity wrapper. So we perform two encryptions actually, the messaging protocol's encryption and the encryption from our anonymity wrapper, which grabs all the ciphertext and the metadata from the underlying protocol. Perfect. Now there's only one problem left to solve. Since everybody shares the same key, anybody could try to impersonate Alice. And to prevent this, we simply add signatures, and that is, with every key distribution, Alice will also distribute a new public key to all the other users, and then she can just wrap her ciphertext, sign her ciphertext and tag. And she also encrypts the signature, so the signature cannot be used to break the anonymity. And yeah, Bob will just decrypt also the signature, perform a signature check, and then can perform the decryption as before. Good. That's how the protocol works. Now we compare this against Signal's current approach, the performance. Right, so Signal uses the sealed sender on top of the sender keys protocol. So we first compared encryption and decryption times for our approach against Signal's approach. And as we see, we only have the anonymity wrapper AW has only a constant overhead for encrypting messages because we only have to encrypt one message because it can be decrypted by all the other group members. In contrast to that, sealed sender and sender keys, we see the group size, it scales with the group size. But yeah, for both decryption in both variants is constant because the receiver only has to perform one decryption. Right, then we looked at the ciphertext size. Unsurprisingly, again, the anonymity wrapper has a constant message ciphertext size because we only perform one encryption, while the message ciphertext size scales with the group for Signal's current approach. Perfect. So now we saw that both the computation and the network overhead for the anonymity wrapper is lower than Signal's current approach. But we also added a new protocol. This means the receiver and sender have to store some more information. So for the sender, that is less than 200 bytes per session they are in, which is fine. But for the receiver, we actually add 600 kilobytes per contact. That means if we have 1,000 contacts, that's 600 megabytes. And this is not really acceptable for deployment, especially if we consider regions where hardware is a little more resource constrained. So to understand why we have such a large receiver state and how we can improve it, yeah, I'll show you in the following. So I'll start with how the receiver state handles out-of-order messages. So let's say Alice sends her first message. Alice and Bob start both with the same key material. Then Bob can decrypt this first message because he has the key material. But it might be that this ciphertext again gets lost. Alice decrypts, derives some new key material and encrypts the second message. Now, when this ciphertext and tag arrive at Bob, he only sees random information. He doesn't have this tag, and in contrast to before, we also do not have this message index. Because before, Bob could use the message index to derive the correct key, right? But that's not possible anymore. So what Bob could do is he could just try and continue in his keychain until he arrives at the correct tag, but this makes him vulnerable to denial of service attacks. An adversary could just send random tags and then that would keep Bob busy with compute. However, discarding the key is also not really an option because we do want to allow out-of-order delivery. So what we do instead, we pre-compute the keys. Signal currently in their implementation allows for 2,000 ciphertexts which are allowed to be received out of order. So we just adopt this number, and Bob can now, and we let Bob pre-compute 2,000 tags and keys, and Bob can then additionally also store up to 2,000 keys. Now, what happens if Alice and Bob exchange new keys? Well, the first thing which Bob does is he pre-computes 2,000 new keys for the new epoch, or for this new chain key, because he needs to be able to decrypt the incoming message from this new key material. But he still has all the pre-computed tags from the previous chain key in his state. And we said Bob can store up to 2,000 skipped keys. So if Alice only sent 2 messages from the prior chain key, then all of these keys which Bob stored are unnecessary. And we do not want Bob to store all these unnecessary tags. So what we do is, Alice can just send, with her new message from the new key material, can send the last tag which she didn't need in the previous epoch, with the previous chain key. So Bob can now, since he stores the tags in order, he can just start from this tag and delete all the remaining tags, and thus clear out storage space. And then he can just discard the chain key, the previous chain key, and merge, basically, the tables. Perfect. Now let's revisit the thread model for a second. We wanted an adversary on the network to not be able to break the anonymity, and we did that because the tag is pseudo-random and doesn't have any relation to the other tags, and the ciphertext is also her assumption on that the underlying encryption scheme is secure. That is also random. Now, temporary state exposure is also okay because we derive a new key for each message, and thus prior communication is not compromised. And with the underlying messaging protocol, we can also agree on fresh key material. Now, since we allow for the state exposure, it would be nice if both the sender and receiver state also don't leak anything about prior or future communication. For the sender, this is pretty straightforward. They only need to store the next encryption key, so that doesn't leak anything. But the receiver stores more information. But it's actually, this information what the receiver state stores is not that much, as I will show you. So the receiver stores this large table basically with the tags and keys. The tags look random. The keys also do not give any information about how they are related to each other. And in particular, we also do not store any indices. So an adversary who reveals the receiver state does not know which messages were or were not received in the past. Great. Now we allowed that Bob can store skipped messages. So it might be that the size of the receiver state differs if there's not many skipped messages. So what we do is we insert dummies so that the receiver state has a constant size, and an adversary cannot make any assumptions on maybe the network conditions or the device conditions. So overall, when an adversary reveals Bob's state, they will only see a constant size of tags and keys, which don't give them any information. Perfect, but still, the receiver state is really large, so we want to improve this. Our first observation is, while the dummy keys are nice and they give a constant state, they can actually take up to 1/3 of the receiver state, which is 200 megabytes if we have 1,000 contacts, which might be a large trade-off for anonymity. So we could just not store dummies if we are not super paranoid. The second observation is that we can assume that our network most likely delivers ciphertexts in order. So the full keys are only actually needed for the tags and keys which are stored at the top of the table. And for the remaining tags, we do not need the full entries. We really just need to know whether the tag is receivable or not. So we could just delete all the keys from this table and just keep the tag. So when a tag arrives, Bob can check if the tag is receivable and then on demand compute the key. But there's more efficient data structures to store this. Right, and we used a counting Bloom filter for that. If you're not familiar with that, that's not a problem. It's basically a data structure where we can efficiently insert and delete items, and lookup and membership queries are very cheap because they basically are just hash operations. So great, now we say that we only store the next 100 full keys, and the rest we put in this counting Bloom filter. And that brings our storage size down a lot if we also don't store the dummies, and that is to 38 kilobytes or 3.8 megabytes for 1,000 contexts, which is much better than the 600 megabytes we had before. Great, so I'll conclude my talk. We saw the anonymity wrapper protocol, which basically takes the key material from some underlying messaging protocol and derives wrapper keys and random looking tags, which are then attached to the ciphertext, and the receiver can use the tag to look up the corresponding key. we compared our implementation, our construction against signals current, seal sender, and sender keys protocol, and we saw that communication and network overhead are both much lower, and especially they do not scale with the group size, but are constant. And since we also managed to shrink the receiver state significantly, Signal considers deploying this approach. Yeah. So this concludes my talk. Thank you.
Do we have any questions in the audience?
At some point, you mentioned that you have to add a signature to avoid, because in the group setting, you could impersonate other users. How frequently are these sign keys changed? Like, how are they long-term, or are they ratcheted in some way? And doesn't that affect anonymity? The fact that you have, I understand it's encrypted, but
Right. So we exchange the signing keys whenever the underlying key material is renewed. So for double redshift, that would be with every round trip. For sender keys, this could be much longer. And it doesn't affect anonymity, because in the receiver state, we actually only store commitments to the verification key. So when somebody reveals the receiver state, we do not see which epoch or which chain key one key belongs to. If that helps.
Maybe I kind of misunderstood, but so this T1, the reason why we want to have this pseudo index is because we don't want to reveal the index I of the message. Is that the only thing that we want to hide right now?
Yeah.
Like, if this, and I guess who is the adversary in this scenario? Is it the server or a person outside of this system?
Yeah, it can be the server or just anybody who monitors the network, yeah.
If it's the server, then when Alice speaks up, then obviously it's going to be the first message, even though if T1 is a pseudo-random value. Because from the server's point of view, when Alice speaks up, and if it's a double rapid protocol, then they always kind of start from index 1 when they speak up. And even if T1 is some random value, would the server learn that it's the first message?
True, if the server knows that it's from Alice, right? Yeah, so anonymous routing is kind of out of the scope for this work. We just wanted to present a generic wrapper.
Right. Okay.
Yeah.
Any other questions?
Maybe a sort of flip question. I think this is super clever, and I mean, you did a really good job of making it a convincing solution. Are there any disadvantages to deploying this beyond the slight increase in states?
It's actually the state increase, so yeah, we have Rolf here, so maybe he can give you later some more insights.
We can go into more detail. So really, it's the state management is concerned, and we need to see what that's going to look like in the wild.
Yeah.
On real devices that have realistic numbers of users and resource constraints.
Does it often happen that 2,000 messages are out of order? Is that a reasonable limit?
That is pretty uncommon. There's a special case, though, which doesn't need the anonymity wrapper when you have a device that's been offline for quite a while. Because every message I'm sending, so I unlink my devices before I leave on a trip, but imagine I didn't. Every message I'm sending to anybody in any group, I'm also sending a sync message to devices so they get it too. So I come home after a few weeks, open the laptop, and I could easily have 20,000 messages coming in on a single double ratchet session.
Maybe I have another question. So having a wrapper for an existing protocol, I guess, creates this additional overhead. Did you also consider a custom solution basically to this protocol where the anonymity is basically baked in and not added on top?
Yeah, we considered adapting the double ratchet protocol. Actually, they have something similar. They have header encryption, but it's not very practical because it's unclear how they assign the header key to the header. So I guess we could modify the double ratchet protocol to basically incorporate our solution.
Thanks. I guess if there's no other questions, then let's thank Lea again.